Welcome to PChem Help, where our goal is to help you to do and understand physical chemistry. I'm John, and in today's video, we're going to be looking at a simple reversible reaction, something like A going to B. And we're going to cover everything that you might want to know about this by getting the integrated rate expressions and relating the rate constants to the equilibrium rate constant. All right, let's get started. So today we will be focusing on a very simple equilibrium reaction where we have A in equilibrium with B. And the rate constant of the forward reaction is Kf. The rate constant of the reverse reaction is Kr. Writing these out separately sometimes can be nice. Of course, A goes to B with Kf and B goes to A with Kr. And the reason I wrote these out separately is just to show you that there are actually two different processes happening here, going either direction. There's two things happening. So let's look at the rate in terms of the reactant A, and we can write that the rate is equal to the rate of change in the concentration of A. And we can also see from the two reactions that this is equal to minus Kf times A and plus Kr times B. And the loss of A comes from this term right here, and the production of A, positive term, comes from this reaction right here. Okay? So we need to decide some initial conditions. Okay? What we're actually interested in is the concentration of A and B at some time t. So we need to determine what's the situation at time t equals 0, the beginning. And let's just say we have A, and we'll call it A naught at time 0, and that's all we have. There's no B in the beginning. So by the law of conservation of mass, right, we can write B in terms of A by knowing that the amount of A plus the amount of B at any time must equal the starting amount. So then we can say B is equal to A naught minus the concentration of A at any time. And the reason we want to do this is so that we can now write our rate, which is dA dt, in terms of only A. So we still have minus Kf times A, and we have plus Kr times B, and this time we'll write B as A naught minus A. So with a little bit of rearranging, we can get minus concentration of A times the sum of both rate constants plus Kr times A naught. And continuing on, we can pull out a term of Kf plus Kr. And we have a minus term times A minus Kr A naught over Kf plus Kr. And you should be able to see how we got to that. Okay? So in this last step now, the last term contains only constants. And so we have now a place where they're all grouped together. Right? All of this are constants. So we're gonna go ahead and call that just C for now. Now we have dA dt is negative K prime times A plus C. And I've also decided that K prime equals Kf plus Kr. I don't want to write all of those out. So now this thing has gotten simplified quite a bit. And the integral here is actually not too bad at all. So rearranging dA over A plus C is minus K prime dt. And I'm going to integrate from time 0 to time t, which means I'm going to integrate from A naught to A. And this is just your typical dx over x kind of integral. The plus c here doesn't change the form of the solutions at all. So we end up with a solution that is the natural log of A plus C over A naught plus C equal to minus K prime t. And we can exponentiate both sides. So we get e to the minus K prime t. Okay. And solving for A and plugging back in for C, remembering that C is equal to a minus Kr A naught over Kf plus Kr. We end up with A equal to A naught over Kf plus Kr times Kr plus Kf times e to the minus Kf plus Kr times t. Alright, now we are done with the first part. We have A. A few things to notice, right? The time dependence only shows up in the exponential term, and it is also dependent on the sum of the rate constants. Okay? So now let's go back and look at B. Recall that B is A naught minus A naught, sorry, and we just found A in terms of t, so now we should be able to find B in terms of t by plugging in the answer that we just got. Okay, I'll show you one step and then we'll get to our final answer. So B is equal to A naught minus A naught over Kf plus Kr. Since we left this on the last screen, I'm going to write it out one more time. I'm just going to leave this as K prime for now, though. Okay? And doing a little bit of rearranging, we get Kf times A naught or Kf plus Kr times 1 minus e to the minus Kf plus Kr times t. So our time dependence and the exponent, that term has not changed, but the rest of the equation has changed a little bit. Okay, so now we have A as a function of time, and we have B as a function of time. Let's consider the situation where time is really long, right? So time is basically infinity. That means it's long enough that the system has reached equilibrium. Okay? And the time dependence, remember, only shows up in the exponent. And so we have basically e to the minus infinity, which is 0. So the time dependence, that part goes away, and all we're left with are the terms out front. So, looking back, A at equilibrium will equal A at infinity, right? And that's going to be Kr A naught over Kf plus Kr. And the equilibrium concentration of B is at long time, and that will equal Kf times A naught over Kf plus Kr. Alright, so let's introduce the equilibrium constant, right? Since our equation is A in equilibrium with B, we know that K equilibrium should be B equilibrium over the concentration of A at equilibrium. So using the expressions that we just had on the previous page, we can easily find that K equilibrium is the forward rate constant divided by the reverse rate constant. Quick note, we also know that at equilibrium the forward rate and the reverse rates have to be equal. That's what equilibrium means. So the forward rate is Kf times AEQ, and the reverse rate is Kr times BEQ. So then the rate equilibrium constant, which again is BEQ over AEQ, has to be Kf over Kr. So there's two different ways to get to the same result there. But this second one would have been a little too easy, right? We wanted to use the results we had. So equilibrium concentrations provide the ratio of rates. Alright, so to conclude, we used kinetics to find the sum of rates, and we used the equilibrium concentrations to find the ratio of rates. So if we know both of these things, we can determine the values of Kf and Kr uniquely. Alright? So that pretty much wraps up everything you would want to know about a simple equilibrium reaction.